For our project, Vidushi Tierney and I plan to explore theoretical versus experimental calculations and trend optimization of metal borohydrides. A wide variety of metal borohydrides have been discovered and characterized during the past decade, revealing an extremely rich chemistry with fascinating structural flexibility and a wide range of compositions and physical properties. Metal borohydrides are receiving increasing interest within the energy storage field due to their extremely high hydrogen density and potential uses in batteries as solid-state ion conductors. More recently, new types of physical properties have been explored in lanthanide-bearing borohydrides related to solid-state phosphors and magnetic refrigeration. Limited research has been conducted on metal borohydrides, providing the opportunity for interesting, creative, and novel molecular designs. In 2019, Grinderslev et al. Conducted a study to discover novel rare earth metal borohydrides with optimal crystal structures, thermal behavior, and magnetic properties for use in crystal and structural chemistry. They also demonstrated synthetic techniques for the creation of the molecules, and overall, the researchers discovered 15 brand new, halide-free, pure, and highly crystalline structures. We aim to answer the following research questions. 1. Does the experimental data obtained for metal borohydrides reflect the results shown in theoretical models? 2. Are metal borohydrides best optimized based on properties of stability, decomposition, and/or magnetism? 3. Does changing the metal cation or space group in a metal borohydride have a larger effect on the molecule's overall functionalities? And 4. What is the ideal metal borohydride structure based on current data? Our project will be split into two parts. We will begin by comparing the experimentally tested structural properties from papers with theoretical values we obtain ourselves to understand the accuracy and reproducibility of results concerning metal borohydrides. Some properties we plan on investigating include XRD, thermal stability, bond distances, and magnetic measurements. Hopefully, this will let us observe some trends in the data that can be useful for the next part of this project.
The second part of the project will be focused on optimizing the physical properties of metal borohydrides by looking at how changes in structure affect measurements. We plan to look into stability, decomposition, and magnetic properties because these tend to be some of the most important aspects when considering the function of metal borohydrides. We will also make sure that our molecules are halide-free due to safety concerns associated with electronics. The variables for this part of the experiment will be the metal cation and space group in the compound. We will submit our most successful designs to the Materials Project database. The proposed method. First, we'll be comparing theoretical versus experimental properties in the article. This includes submitting the 15 crystal structures described in the article to the Materials Project database using PyMatGen to get theoretical data. We will also be generalizing trends among metal borohydrides. This includes obtaining a data set in Python of all metal borohydrides in the form MBH4X. We'll also be screening for volume, magnetic properties, band gap, stability, etc. And also, we will have to see if certain metal ions or space groups show outliers in physical properties, for example, magnetic properties. Proof of concept. So far, we were able to use a template with the PA3 space group and substitute it in CE in order to model one of the new 15 structures, CEBH43, and the submission number was 150079. We will also be modeling the other 14 structures similarly from scratch. Also, part of the proof of the concept was some of the code that we used. This is the code that can be used to search for various metal borohydrides if we want to analyze trends on a larger set of data. And this example specifically searches for monometallic borohydrides. This example was easy because we found the right template, but it will be harder to do the same thing for the other molecules for their appropriate space groups. But we will be using Patrick's YouTube video series to get more information.
So in the more immediate future, we need to create the rest of the 14 crystals and submit them as soon as possible to the Materials Project database. There weren't templates with the right space groups already uploaded there, so we have to make them from scratch using Patrick's tutorials. So that's something we will do in the next few days. Then, potentially, we might further explore the effects of different space groups on the physical properties of borohydrides, because one question we were wondering is whether the space group and structure has a greater impact than the rare metal or like the element composition of the compound. This might also involve creating crystals that aren't already in the materials project database, so it is something we will look into sooner rather than later. Depending on how far we get with all of that we have already, there's a lot of room to expand even further, since borohydrates are quite a comprehensive set of compounds. This article that we found on the Royal Society of Chemistry has a comprehensive list of all types of metal borohydrides and trends amongst different subgroups of them. This includes bi- and trimetallic borohydrides and anion substituted compounds. This might be a little beyond the feasible scope of our project because it's very extensive, but if we want to broaden our perspective, that is a potential direction we could look into.